Once again, Lenz's law, the induced current as a result of this EMF flows in such a direction so as to oppose the change of flux that is taking place. Right? That is Lenz's law. So make sure that you understand the law itself. The induced current, whichever way it flows, it is flowing in such a way to oppose the cause. That's basically it. Right? So I think I've written down in words. Now, I think I gave you also the coil, and I told you, like, if I bring a magnet closer, what will happen in the coil? If I bring a magnet closer, any flux that's going to change in there is going to change in such a way that it will try to oppose the cause. The cause is the incoming magnet. So therefore, if a north pole is coming in, to oppose the north pole, the field has to be pointing in this direction, and so the current will flow in such a direction using a right-hand grip rule. Right? So that way you can understand which way the current is going to flow. Right? Yeah. So some other examples I can say is, if I have a loop of wire there, and if I have a current flowing in a wire here, is there a flux in this coil right now? Is there a magnetic flux in this coil right now? Yes. Which way? Use your right hand grip rule. You can see that the magnetic flux is coming out. The magnetic flux is actually coming out. And you know that flux is equal to the magnetic field that's present over here times the area of this loop. If I'm going to say only one loop is there, then that is the flux. And which way is the flux? Towards you. And so, which way will the current be flowing? Right here. Which way will the current be flowing in the wire, in the loop? Which way will the current be flowing in this wire? Will there be any current at all?
We have the resistance.
No current at all. Why? Because there's no change in the flux. What did Faraday find out? He found out that a current is flowing only when there's a change of flux. So right now there is flux, but it's not changing. So which means there is no induced current existing. Because induced current only comes in to oppose something else, right? Now let's say I'm going to turn this current off. This current that was flowing here, I'm just turning it off. As soon as I turn this thing off, what's happening to the flux here? It's dying, right? Which direction it is pointed originally? Towards you. And it is weakening and dying. So what will the induced current do? Trying to keep it. Good word. It's trying to keep it. Which means it will try to restore the magnetic field. Which means this way, the magnetic field this way, it tries to support it or prevent it from failing. And therefore, the current has to flow this way in order to produce a magnetic field supporting it. So there will be an induced current that way. Make sense? So there will be an induced current, but not for a long time, as till the magnetic flux dies off. Fine. Yeah, because this current stops abruptly, which means there's a change of flux. And this current will be a strong current that's flowing here because the change of flux is a very sudden change. So time is very short. And because time is very short, whatever change of flux is taking place, the EMF is going to be high, and therefore the current is also going to be equally high. Make sense? Now, giving you another scenario. Suppose there is there's no current right now. That means no flux here, right? Which means no current here. Nothing is happening. As soon as I turn on this current, which way is the current in this loop? As soon as I turn on the current, which means as the current is being established here, which way will the current flow? Now you work it out and see which way it goes. Feel free to use your right hand.
Clockwise.
Clockwise. Let's see how. This produced the magnetic field in the downward direction, and that you got by right hand grip rule. So the induced current is always trying to flow in such a direction to oppose the cause. So that is what you see there right now. And this current is growing from a small value to a larger value because I turned it on. So the current is growing. That's my way of saying it's growing. So small current to a larger current. Okay, so it's growing. That means this field is growing. Now the induced current will flow in such a way to oppose that growth. So the current will flow in such a direction, not this way, but this way. The current is going to flow this way so that the magnetic field produced by the induced current will flow in opposing direction to oppose the cause. The cause is a growing magnetic field in the downward direction. Therefore, to oppose a growing magnetic field in the downward direction, it tries to flow the other way around. So the current will flow this way. And that won't be flowing all the time. It will flow only for the time these changes are taking place. And after that, everything's over. Okay? Got it? Another example. Suppose you have two railings connected together here, and a rod is placed over here, and a rod is placed over there, and there is a magnetic field applied into the board. There's a magnetic field applied into the board. As soon as you turn the, no, okay, right now, is there a flux linkage by this part of the conductor? This side is open, but this conductor is a loop, right? Can you see the loop? This is a rod that is sitting on a rail like this. So there is a closed loop, and there is a flux through the closed loop. But there won't be any current because there's no change of flux. But suppose I turn this thing off. If magnetic field is turned off, as soon as the magnetic field is turned off, what's happening to this flux of BA? It's going to go down. So what is going down of these two? B is going to go down. B is going to go down. So which means, which way will the current flow? In order to stop it from going down, which way should the current flow here? Clockwise or counterclockwise? Clockwise. So the magnetic field, you need to support it. So the induced current will flow clockwise this way. Now, when the induced current flows in that manner, look at this conductor. Look at this conductor. There is a current flowing in the conductor, and it's placed in a magnetic field. So which way will it experience a force? Use your left-hand rule, Fleming's left-hand rule. Current is down, magnetic field is in. Which way will it experience a force? So what will happen to this rod? It will roll off. It will roll off. Or think of it in a different way. Think of it in a different way. Lenz's law. Flux is dying. Flux is dying. Why? Because B is dying. So how can you try to prevent it from dying? By increasing the area. Is that right? If B is dying and you want to retain the flux, induced current will flow in such a direction to retain the flux. So what happens to the area? Area is supposed to increase. And that's exactly what you saw. Why is the rod moving that way? Is to increase the area. Make sense? And this whole thing is basically what we call as a rail gun. This is a rail gun. You turn off the magnetic field and this thing shoots off on the rail. So a rail gun's main thing is you have something that can slide through electrical contacts. And then you turn on the magnetic field, turn it off, and it shoots off. The idea is Lenz's law. Okay, you can see how this works. All right, so let me explain it again. Let me explain again. So what is happening is this is a magnet, and think of these as multiple little loops like that. They're all closed loops with hardly any resistance. So this is a closed loop. So when this was falling, as it was falling because of gravity, it was subjected to changes of flux. And so each and every section where it is falling was inducing a current. And the current is induced in such a direction to oppose whatever is causing it. And so as the magnet's approach is basically the main cause of the induced current flows in such a direction to push it back. And so, well, can it stop the thing? Because if it stops the thing, what will happen? If it stops this thing from coming down, then there's no flux change, and so therefore gravity will pull it down further, right? So it will flow at a certain speed depending upon how much induced current is flowing and how much opposition is taking place. So the current will flow here, depends. Make sense?
Could you put a current in it and then like accelerate the whatever's falling?
Accelerate the object?
Yeah.
If you put a current in it in the favorable direction, yeah, it's possible. But then you cannot have it this way, because it has to be separate coils, and the coils must be all separate segments. Because if you are actually making current flow one way, the object which is actually going down can be pulled in as well. So you need to, if you want to accelerate it, you need to pull it down with a larger force. And that means you need to make the current flow differently as it goes down. It needs different coils, and it's not that easy. Yeah, it can flow under. I mean, it can fall under gravity normally, but a magnet. This is what happens. You can have a copper tube, that's fine. But if it's an iron tube, what will happen is this thing will get stuck. Right? It will stick to it. So this is not sticking to it. This is falling. And it's falling straight. So when it's coming down, it is coming down straight. I don't know where it is. I can't see. But it is somewhere. It is somewhere here. If I keep it at an angle, it will take forever. But it will come down. It is coming down. You can wait. It is coming down, but slowly. Slow.
Your eyes check it's coming out.
There it is. So it's coming down so slowly because when it's tilted, the gravity is only mg sine theta, right? And so only a small, whatever change is taking place, the current induced here is just able to oppose it further, and so it can reduce the acceleration much more. So overall, the acceleration is much smaller than g itself. All right, here, pay attention. Here's a coil, and when I send electricity to it, it actually gets magnetized. Now this is a core. As you can see, the core is made of a bunch of wires. Okay, it's iron core. So it's a bunch of wires put together, and that forms a core. So if I just plug this in, it is going to get magnetized, but it is not a magnetism in one direction, it's going to be in both directions because it's alternating. Magnetic flux will flow this way first, and then this way, and then that way, and that way. It cycles how many times per second? 60 times per second. That's 60 hertz power supply, right? So when you actually plug it there, the alternating current over here will produce alternating fluxes here in this core. And if I put, say, that metal ring down here, the metal ring is going to be subjected to those flux changes. So see what happens when I plug it in. See what's happening here. Nearly missed the lights. Nearly missed the lights. That would have been bad. All right. Yeah. So, what did you see here right now? Why did it shoot off? My question is that. Why did it shoot off? Why did it go up?
Let's do it again. Point it out this way.
Okay, you want to do it again?
Game ready.
I'll point it to you then. Take the catch. Forward.
I'll catch it.
Catch it, don't sit. Okay, Nick, it's for you.
Which one?
Perfect.
That's
That's a good catch. All right.
Yeah, my son catches. Yeah, where the couch today?
So, now explain. So why is it shooting off from here? Anyone to explain it? Yeah. Explain. Same thing. We are talking about Lenz's law, so that's how it is to be explained. Say it again. So, go ahead. Same technique as the other one. It's almost the same technique. Look, this is the rule. The same as the tube. All right, so since it is alternating, first the magnetic field is possibly going that way. So the induced current is going to flow the other way in this so as to produce opposition, correct? And opposition means it's going to be pushed out. Now the cycle changes. The current here is now going to flow the other way around and create a magnetic flux the other way, but this current is also going to flip, creating an opposition again. So when induced current is flowing here, induced current is also going to flow here alternating. It's going to alternate in such a way that there is opposition all the time. And that's the reason why it can, experience that huge force, and even beating gravity sort of force was strong enough to take it out. You want to do it again? Let's see if I can take the catch once again. Got it. All right, so, and if I just keep it there, you see that? It is sitting here. It's not falling. Huh? Yeah, and when I took the power off, it came down. This is called magnetic levitation. You heard about magnetic levitation? Yep, that's what it is. Magnetic levitation. Induced currents in the coil flows in such a direction to oppose the cause, and therefore you can actually let it float. You saw that floating thing. Now what will happen if I just hold it here? Remember, there is a current flowing in this thing. If I hold it here forcefully, the current is going to be extremely strong. Why? Because this hardly has any resistance, right? So let's say the EMF generated here is, the EMF generated inside here, if it is just, say, 4 volts. And suppose the resistance of this is 0.1 ohms, which is actually far less than that. But I'm saying if it is 0.1 ohms, what is the induced current? 40 amperes. Going through this, what will it do? What will a current create? Heat. So this will get hot. So what I'm going to do is I'm going to keep it inside here in the field, hold it there till it becomes hot, and then I'm going to pass it on to you. Who's the first one to receive it?
Let's go.
Just letting you know it will be hot. I am passing it to you, but it will be hot. Take care. I'm holding it there till it gets hot. Yeah. It is now really hot. What? Take it, feel it, and go, let it go.
Right through it. Pull it through it.
Don't drop it! Don't drop it! How did it become hot? I'm just holding it there, so the change of flux is actually really high, causes EMF strong enough here compared to here, and then the current induced here is going to be severely high, and that huge current is what caused the heating effect. So much heating effect. You can see it can be used as a hand warmer, right? Especially these days. You can just use it as a hand warmer. Yeah.
If you held it there, then released it, would it go higher than
If I left it here and then left, here,
down at the bottom, like higher than the?
it's supposed to be doing exactly the same thing as what will happen if I just plug it in. The most effect will be seen when you just plug it in, because from no flux to suddenly some flux, that will create a huge amount of current momentarily, which will take it off. So if I leave it from here, it will just bounce only till here maybe. Okay. I was holding it here and I held it for some time and then passed it. Some of you are doing that. Now, instead of this, I'm going to put this one here. And right now it is an open circuit, and see what happens when I connect it and make it closed. Watch the gap here. I'm just kidding. All right. You see what's... All right. I don't want to trip. What was happening over there? What was happening in the previous class? They all got scared really bad. Now watch this as I touch this here.
Oh. Bro. Don't play me like that. Don't play me like that. Jesus Christ.
Now watch this as I touch this here.
Oh. Bro. Don't play me like that. Don't play me like that. Jesus Christ.
I thought we were going to have to get the first aid kit out again.
Yeah, so what is happening over here? There was a strong current here. That's why you can see it's all eaten up. The copper is all gone. When I was touching here, there was an EMF induced. The 110 volt over here is creating a voltage of roughly 2-3 volts over here, which is safe for me to touch. So 2 volts or 3 volts is not going to do anything to me. So I'm not getting any shock by touching this. But when I touch here, this entire coil becomes low resistance, and so the current will be pretty high, and so you saw the sparks jumping across, and the heating effect is so high down here that it is melting the copper. All right? Got it? And all these are connected to the same equation. That's a beauty. All this Lenz's law and all those things are connected to the same equation.
Nick, did you think there's a lot of information was fine? So you had to say it again.
Now this is the same thing. I just pulled the cord down. See, the cord is right now inside. You can see the cord right there. Now if I turn this on, yep, there is a magnetic field coming out from here because this is creating a magnetic field right there. Now these are insulated wires, that's why when I touch it, nothing is happening. But what is going in is 110. So there is 110 in these wires, but it is covered up by cotton and stuff like that, so I don't get it. So this place is the place where you have magnetic field coming out right now. So there's a change of flux taking place right here. So if I have another coil such as this, then if I place it there, you can see why it is trying to jump off. It's not sitting, it doesn't want to sit there. It's because what is induced here? Current. And that current flows in opposite direction. And so it doesn't want to settle down there because it is pushing it away. Now, so what is flowing here? Current. Now here is another loop. That is another loop just like this. This is another loop of wire but multiple turns and connected to a light bulb. So what will happen if I take this close here? See this? So this is electrically not connected but magnetically connected. This is
Wait, is this how they're doing like the wireless phone charging? Oh my goodness.
This is exactly the technology of wireless phone charging. Not a big deal. It's just that they just made it small enough to be able to do that job right. But this is what it is. But the strength of the field produced by from here is not too strong. That's why the number of turns are very small and all that. But in your wireless charger, the magnetic field is produced, and your phone has a coil like that, which is connected to your charging circuit. Your phone must be having a coil or a loop, and that is what causes that. Yeah.
It stays on because the alternating current.
Continuously changing alternating currents produces continuously changing induced currents in alternate directions. And see this. Now, what you can see over here is magnetic field is able to pass through the glass, and the coil is intercepting those magnetic fields and therefore inducing the current, and the light's glowing there. So if you want to light up something underwater, there it is.
It's because if you take fire and you push it under the water.
So that's the basic idea of wireless phone charging. Any questions? All right. Okay, let's continue. Are you ready? Now let's take this. There are two rails. There are two rails again. And a magnetic field is applied into the board. A magnetic field is applied into the board. And there is another conductor placed here. Okay, so just like the previous one was closed on this side, but this is a conductor sitting on the rails. Now, these conductors made up of electrons, charged particles, right? Electrons, free electrons are here on this. So there are a bunch of free electrons on this. If I force it to move this way by applying a force, if I'm going to force it to go that way, I'm going to carry these electrons that way, correct? So now it becomes moving charges in a magnetic field. What will happen to those electrons is my question. If I'm going to drag the entire conductor to the right, isn't each electron going to be shifted to the right, which is equivalent to current which way? That way. So the current is that way, and magnetic field is in. So which way are the electrons going to drift? Down. So what will happen is the electrons will start drifting from here downward. So it will collect more electrons over here and less over here, and that will create a potential difference. Basically, it's going to create an EMF, electromotive force, because the electrons are clearing off from there and then collecting itself here, because as you dragged it, all the electrons were subjected to a force in the downward direction, so they started moving down. When they started moving down, it creates a potential difference, positive, negative. Yes, question? Somebody raise hands. Is that okay? So it's positive on this side, negative on this side, but it won't let current flow through. For a current flow through, you need this circuit to be completed. So now, the EMF is available, and there is a resistance available in the circuit. So will there be a current?
Yes.
Which way? This way? This way? This is the induced current. We didn't send it. We didn't send it. That got generated. This is the induced current. The induced current got generated in that direction. Why? Because I moved the conductor this way, and it is placed in a magnetic field. Now, to tell you which way the induced current can flow in a moving conductor, Fleming's right-hand rule. Now, use Fleming's right-hand rule, apply here. What is this thumb indicating? It is indicating the force that you applied, or the motion, direction of motion. This is the direction of motion. This is the field, and this is what? Not the current you sent, but the induced current. The difference between left hand and right hand is this. On the left hand, you are sending a current in a conductor, placed in a magnetic field, and the conductor experiences a force. What is happening here? You are not sending the current. You are moving the conductor that way, and induced current flows in this direction. So, look at that. Force is, you're forcing it to go this way, and the field is inward, so the induced current is upward. So this will help you to find out that.
Sonic forces with which way?
So it's like this.
Is that clear? So Fleming's left-hand rule, when will you use Fleming's left-hand rule? To find the force on a conductor carrying current. You should write it down clearly. Left-hand rule, when to use? Left-hand rule will tell you the force on a current carrying conductor. Fleming's right-hand rule is used to find the direction of induced current in a conductor, in a moving conductor. So Fleming's right-hand rule is going to help you to find the direction of the induced current in a moving conductor, because that one is a force on a current-carrying conductor. Yeah.
Okay, what are the different fingers again?
The same things, FBI, FBI. It's the same thing. But in the left-hand rule, F is something that comes as a consequence, because you're sending the current in a magnetic field. In the right-hand rule, F is not a consequence. F is what you are pushing to, right? You are giving this. This current is a consequence, which is called the induced current. So if you're looking for induced current directions, right-hand rule. It's easy to use both of them. And so whenever you want to find out the force on a current-carrying conductor, use Fleming's left-hand rule. Whenever you want to find the direction of induced current, then use the Fleming's right-hand rule. It's not over yet. Hold. If I apply a force F, what should happen to this conductor? It will, if I'm moving it with a force F, it should what? When you apply a force on anything, what should happen to it?
Accelerate.
It should accelerate. But look, when I'm applying a force this way, I'm going to be able to move it with a constant velocity. Now let's see why. Look what's happening here. Because I'm moving it to the right, an induced current starts flowing, right? But when an induced current starts flowing in a conductor, you can apply this now. Force on a current carrying conductor. Because there is a current in a conductor flowing upward, use your left hand rule here. The left hand rule will tell you current is upward, magnetic field is this way. What is this? The force. So when you apply a force that way, you have to fight this force. You have to fight this force. And that is according to which law? Lenz's law.
This guy.
Lenz's law.
Newman's.
Newman's law. Lenz's law. Look at that. This is a force of opposition that you are supposed to overcome. What's the net force here? 0. So you are actually moving it with a constant velocity. Because if you try to push it harder here, this will also go up because the current will be higher now. You understand? So if you are pushing it with a certain force, you are going to fight this force, which according to Fleming's left-hand rule is BIL. And if you are applying a force F and moving at a constant velocity V, there are two things that are happening here. Are you doing work by dragging it? And that work is seen in what form? Electrical energy. Make sense? Okay. So since you're doing work, electrical energy, there's a connection to it. And you can see here, the mechanical work or the mechanical power that we put in is equal to the electrical power generated. This is basically a generator. This is a generator. All you did was drag this conductor and you're creating electricity. So it's a generator. So mechanical power should be equal to electric power because energy is conserved. Energy cannot be created nor destroyed. If you're creating electrical energy, electrical power, then mechanical power needs to be expended. What's the formula for mechanical power? You done it last year. Mechanical power. What's power? Work over time. So what is that? All right, here we go. Work over time is power. And work is force times displacement. What is displacement over time? So it's F times velocity. You did it last year, forgotten already? That one. This is a mechanical, so mechanical power is F, the force that you applied, times the velocity. How fast are you making it go? That one. Should be equal to electric power. What's the formula for electric power? Current times the voltage generated is E, so EI. Now, what is F? How much is the force that you have to apply to move it at a constant velocity? How much is this force that you have to apply to move it at a constant velocity? BIL. So BIL V is equal to EI. Then I's are out. What you see is a very important equation. The EMF induced in a moving conductor is BLV.
Easy.
So if you have a conductor of length L moving with this speed in a magnetic field, it's going to generate an EMF, which you can use it for producing currents. Clear? Let me know if you have any questions over here. Simple equation, we derived it, and you can see all the physics behind it. You applied a force in order to fight this force, which is BIL. and that's why you're able to move with a constant velocity. And mechanical power is Fv, which is BILV, and is equal to the power generated, EI. And so EMF is BLV. So any conductor moving in a magnetic field will develop an EMF, which is a magnetic field here in this room. This way?
Yep.
This is a conductor. Come in. Imagine if I have a conductor and if I'm dropping it like that. If I'm dropping the conductor this way, will an EMF be produced here? Will an EMF be induced across the tips? Yes. Because magnetic field is this way. So that's your right hand rule. This is moving downward. So your thumb indicates downward. So find out which way is the induced current. You have to use Fleming's right hand rule. So it is going down, magnetic field is toward this way, and it is going down. So it is this way. The induced current is this way, which means which terminal is positive and which one is negative. That's positive and that's negative. Remember, this is a generator. This is a generator. So if current is actually coming out from here to the rest of the circuit, that means this must be the positive. Make sense? Inside the battery, current always flows from negative to positive. Get it? Yeah, see, if you have a battery like that, if you have a cell like this, and if you connect it to a resistor, the current is going to flow out of the positive and come like this. But how is the current flowing inside the cell? Is this way. So even though this is positive and that's negative, inside the cell is going to flow from negative to positive. So when this was going down, the induced current was trying to go this way, which makes this side more positive, and so the current can come out from there. Get it? Let's take an airplane. An airplane is flying in the northern hemisphere. So imagine the airplane is flying in the northern hemisphere, where the magnetic field is directed which way? See, you have to include the dip also, dip. So in the northern hemisphere, it's going to be dipping downward, like here. In this room, the magnetic field is not in that direction. Technically, it is that way. It is tilting this way because of the angle of tip. It's not purely horizontal. It's like this, which means it has two components, a vertical component and a... So in the northern hemisphere, let's say there's a plane that's going there. That's a plane. That's a plane that's going in the northern hemisphere and flying in that direction. Now remember, this wing is a conductor. It's made of metal. It can conduct electricity. So this is a conductor, and it's moving in a magnetic field. Which field? The vertical component. Which way is the magnetic field here? Yeah, we are only interested in the downward component. We are not interested in this in the same directional component. All right. Now, which way is the wing moving? To the north. The wing is moving to the north. So which way will the induced current be set up on the wing? Well, current is not going to be produced, but EMF will be produced. For current to be produced, you need a complete loop. But there's no complete loop. This is just the wing. So when the wing is going like this, which way is the induced current is my question. So the magnetic field is going in, magnetic field is going downward, and this conductor is moving up. So magnetic field is going in, and this wing is moving upward. So the induced current is this way. So which wing tip is positive, the west or the east? That's positive, that's negative. You get it? And there will be an EMF induced. Now what is an approximate number for magnetic field of the Earth?
5.5.
So let's say 5.5 times 10 power, no, it may not be 5. Okay, it may not be 5.5, well it may be 5.5, but because of the dipping action, it's only a component, right? So let me just give it a number there. The vertical component of the magnetic field is 10 power minus 5 Tesla. That's a vertical component. And what do you think is the length of the wing for a big enough plane? The wingspan? Like 40 meters, 50 meters? Something like that. So let's say 50 meters. 50 meters wingspan. And then the speed, let's say it's flying at 720 kilometers per hour. Now you got to change it to divided by 3.6. So change it to divided by 3.6. That is 200 meters per second. Now plug all these three in and tell me what's the EMF. Three times 10 power minus 5 times 50 times 200. .3 volts. 0.30 volts. The EMF is pretty small, but it is there. It is there. The EMF is there. So across the wingtips, there is a potential difference, plus here and minus here. Now let me ask you another question. Suppose you have a light bulb which can glow with 0.3 volts. If you have a light bulb which can glow with 0.3 volts, so this is positive and that's negative 0.3 volts, right? If I connect a wire from one wingtip on the top of the plane, I put the bulb. You know what I'm saying? So that's a wing. That's a wing. That's a plane. So this is a wing, and he said this side is positive and that side is negative. What I'm going to do is, if I take a wire from here and connect it, and I put the light bulb here, and then I connect it back here, will the light bulb glow? It's a light bulb which will glow if given 0.3 volts. My question is, will that light bulb glow? If yes, answer. If no, reason is more important. Will that light bulb glow? Think about it.
No, because the wire is also a current moving, or like a conductor.
That's the answer. This wire is also another conductor cutting flux lines once again. So just as the wing is establishing 0.3 volts, the wire is also a different conductor, also cutting lines, and therefore will induce 0.3 volts. So it's like connecting two batteries like this. So the bottom one, the bottom wing is a battery, and the top one is also another battery. Both are 0.3 volts and 0.3 volts. You're connecting together, nothing is going to happen, because the net EMF is. Now, if you want to make the light glow, there's only one way to do it. The wire that you're connecting should not cut lines. So maybe you can have wires dangling to the ground. I mean, thinking further. Just have flexible wires down to the ground, put the bulb down here so the wires are not cutting the flux lines, it's the wing that's cutting the flux lines. Then possibly. But otherwise, no chance. So you cannot use the wing, the EMF induced on the wing tips to generate anything, because whatever you're going to put there as connecting wires, they're also going to be subjected to the same change of flux. Make sense? So when you have flux being cut or flux being changed, you will have induced EMFs. Okay, stop it at this.